All right, folks, take two of our 3.4 video here. I nearly started recording again with my microphone not activated, but here we are, and I'm hoping you can hear me this time. Now, here we're working with transformations of cubic and quartic functions. The way this lesson is going to work, we're going to recall from our chapter 1 work. We're going to review some of that a little bit, and we're just going to break down a new approach to graphing a transformed function. You already have one approach, that's using your mapping rule. We're going to try a new one. We're going to call it mapping by transformation, or graphing by transformations rather. And we'll try and use this. I will encourage you to learn this approach just so that you know which approach you prefer, whether you prefer to use your mapping rule or whether you prefer to graph by your transformations. But either way, I do encourage you to learn it first before you choose to prefer graphing by your mapping rule, if you do so prefer that. Now, you might notice this particular beginning of the note. This is copied 100% directly from our note in section 1.4. So I'm not going to take any time on that because I know you've already been through chapter 1. You are responsible for being comfortable with that material. If you're a little bit uncomfortable with either our function notation of the transformations or the transformations themselves, then I encourage you to go back and take a look at that video. That video is posted. Now, again, we do know how to graph with the mapping rule. We're going to go through, we're not even starting with a cubic or quartic function. We're just going to start with one of our newer functions, with an absolute value function, and we'll try and piece it together by its transformations. Now, when we're doing so, just like when we use our mapping rule, we need to follow our order of operations. When we're graphing by these transformations, our operations tell us that we're going to work with our reflections first. Now, we could be a little bit, we would have a little bit of leeway if you wanted to work with your stretches and compressions first, you could, but I like to keep it nice and simple. So we will start off with our reflections, then we'll work on our stretches or compressions. And when you're working on these, obviously, just like with your reflections, your translations, every single each of these categories of transformations, each of these categories has two different types of transformations, right? Horizontally and vertically. You can reflect vertically or horizontally. You can stretch or compress a function horizontally or vertically, and you can translate a function horizontally or vertically. Now, when we're working in here, first we'll work with our reflections. It's not too challenging to work with a couple of reflections at once if we so choose, but working with a horizontal stretch and a vertical compression, or any combination thereof, it's often easier to deal with those separately. So you're going to see us work with those separately. I know it says there are 3 steps, and I know I'm droning on before I go through the example, but I promise this will make sense in just a moment. But lastly, we're going to go over our translations as the final stage in our transformations. So we're going to look right here at this absolute value function. Now, this absolute value function, it is a function that you have seen before, obviously. Here we're working with some transformations. These transformations, if we care about the letters, that is a equals -1/2, k equals 2, and let me see here, q equals 2 as well, where q equals the 2 on the end, k equals the 2 that's happening inside the function. Now, again, that's a little bit of an aside. We don't necessarily care about that. We just care about which transformations are going on. And before then, we care about which base function we're working with. So this base function here is y equals the absolute value of x. You can see where we're going to head next with these colors down here. So y equals the absolute value of x. We're going to start off and we'll sketch that first. Nice and simple. That's it's a linear function that looks like y equals x on the right of my y-axis, and where my x values are negative, then it's a linear function where y equals the -x. Perfect. So this is nice and straightforward. I'll call that number 1. That is our base function down here. Now, next, we're going to work with, according to our order up here, we're going to work with our reflections. So here, there is one reflection. It's a vertical reflection, and that is, it's a reflection over the x-axis. So here, I'm going to work with exactly the same points on my function, exactly the same shape on my function, except this time it's going to be going in the opposite direction because it has been reflected over my y-axis. So I'm hoping you're following this here. I do think it's pretty straightforward. I think it is beneficial to look at these functions directly from their transformations. So we'll call this one sketch number 2. And our equation down here would be y equals negative the absolute value of x. So you'll see gradually we will build this equation here just one transformation at a time. Now next we're working with our stretches and compressions. If we have some horizontal and some vertical, if we have a horizontal one and a vertical one, it does not matter which one we go for first. We're just going to work from left to right. So that is, we'll work with our vertical compression here. This is a vertical compression by a factor of 1/2, and looks like we're working with green this time. That means our equation when we're working with our full A value here, y equals negative 1/2 times the absolute value of x. Well, that is, I am vertically compressing this by a factor of 1/2. So that means if I consider any point on this red function, I can take its y coordinate and I can divide it by 2 to find that point. That's how I thought about it with the mapping rule. Here, I'm going to view it as if I'm grabbing my function on the top and on the bottom, and I'm squishing it so that it's getting compressed by a factor of 1/2, so that it takes up half of the vertical space that it did before. One more time. Oops, here on the left side, I'm working with something that looks like this. Now I can also consider that with my absolute value function. With my second function, the one in red there, my slopes were still positive 1 and negative 1. In green here, my slopes are positive 1/2 and negative 1/2, where you can see at any single point, this point, its initial y value was negative 1, and it gets transformed, it gets compressed, so that now its y value equals 1/2. So you're seeing here, it's just like we're working with the mapping rule. We're doing the same things, but this time we're transforming the entire function at a time, as opposed to point by point. Now next in our equation, which color are we going with here with some orange? So we still have, we're not finished with our stretches and compressions. You can see that I have a horizontal compression also by a factor of 2 here that I'm working with. So if I'm horizontally compressing this by a factor of 2, you might be able to predict what this one's going to look like. So try and visualize it here. From the green function, I'm horizontally compressing it, so it's like I grab it on the left, I grab it on the right, and I push them in together. So it's horizontally getting compressed, so it's going to take up half as much space horizontally as it did before, and actually it will look exactly like my red function did. Now you might be able to see algebraically how that adds up here as I try and get the other half sketched in. There we are. You might be able to see algebraically, sorry folks, bear with me, algebraically how this 1/2 on the outside of the absolute value sign and the 2 on the inside of the absolute value sign will cancel one another out. So that's how these transformations, now they won't always cancel out like that, and you will notice that when you're working through example B over here on your own, but sometimes they do cancel out, and in which case you'll notice here in and along the process from 1 to 2 to 3 to 4, you'll notice that our function might look the same as it once did. Lastly, we have a final transformation. This is a translation, and it's 2 units up. So here in purple, our final function looks exactly like the question was, the problem was asking about. And in this case, we're taking this orange function here, and we are transforming it, translating it 2 units up. It should look something like this. So there you have it. If you prefer to graph by transformations, absolutely do so. I do encourage you either way to try and graph by transformations, just to familiarize yourself with the concept a little bit. For 1B here, you might find it useful for you just visualizing what's going on sometime in the future. Now, I know this lesson is talking about the transformations of cubic and quartic functions, and I realize we're already 8 or 9 minutes into the video, and I still haven't talked about them. Please don't fret at this point. I know you've seen the length of the video. It's not going to be very long. our cubic and quartic functions, it's nice and straightforward how we can apply our previous knowledge of transformations to these functions as long as we know what the base functions sort of look like. Now, as an activity, what I encourage you to do is use your favorite graphing calculator, likely that's Desmos. I want you to try it out, but first try and predict what your functions are going to look like. So we're starting with f of x equals x cubed. This one in particular, we have worked already with it so far, but hopefully we can work to gain a little bit more understanding. And I would like you to try and sketch these as best you can. Try and predict what they'll look like and compare them to their equations once you put them in Desmos. And I'm going to leave all of them for you either as you go through this video or in class tomorrow. Next, though, we're going to start applying our analysis skills to that really you started learning in grades 9 and 10 to handle these cubic and quartic functions now that we're in grade 12. So here we're going to work with a quartic function that looks like this. I know it's quartic because the degree here is 4. Degree equals 4, that means it's a quartic function. And this is shown, you might recognize this form as in vertex form in when you were working with a quadratic. The difference is this time it's a quartic function. Now, either way, what's happening here is we can view this now that we're in grade 12 as by its transformations, right? So an a value of -2, a q value of 32, a p value of 5 in here, and we can piece it all together as we work through here. So we'll start off, we want to find the roots of this function. We can do this algebraically here. So we can set our y equal to 0, or set f at x equal to 0. And that is, I'm working with 0 equals -2 times x minus 5 all to the power of 4 plus 32, nice and easy. Now this should be completely review at this point, right, just in terms of our algebraic process here when we're isolating for x. So I'm just going to try and talk over it as I perform this, but I'm not explaining every single step because, again, you should be able to handle something like this honestly in your sleep by this point. If you can't, that's okay. This is the only part where a bit of a new step came up. It just means you need to practice if you're not feeling that comfortable here. So now we need to take we need to avoid erasing all of our work. We need to take a fourth root of 16 and of both sides here in order to perform the opposite operation of putting something to the exponent for. If we're doing that just like when we worked with square roots, folks, we need to make sure we're working with a plus or minus sign. Maybe let's emphasize that a little bit more. Okay, so with any even number root that we're taking, you want to make sure you're taking the positive and the negative roots. Working forward, that is x minus 5 without any exponents on the right-hand side. Now on the left, if you would like, if you're not seeing it right away, you might see it right away. That's great, in which case fast forward about 15 seconds. But if you don't see it right away, 16, I know, equals 2 times 2 times 2 times 2. Right, and if that's the case, then 16 actually equals 2 to the power of 4. And if this is the fourth root, then those cancel out. I'm working with plus or minus 2 equals x minus 5. Still isolating here, that is x equals 5 plus or minus 2, and that is x equals 3 or x equals 7. So these are my two roots. These are the two roots, remember what we were doing here, of the quartic function up above. So we can sketch those in right here, x equals 3 and x equals 7. And then we need to ask ourselves, so just like a quadratic, which is an even degree polynomial, a quartic function, again an even degree polynomial, will have n behaviors going in the same direction. So it's going to be like this function either opens up or opens down. We can learn about that from our a value. Our a value here is -2. So because it's less than 0, this function is going to open down. Maybe I'll write that here. A is a equals -2, which is less than 0, so it opens down. Perfect. Now lastly, what we can find is we can find a vertex, and that vertex is given just by the transformations being applied here. So our vertex should be at 5 and 32. I'll call this 32. It's very rough here, folks. So we're working right here. It opens down. Something shaped generally like this here is how we're working. So again, this kind of problem like this, very, very similar to those sorts of problems that you would have solved in grade 10. The only difference is in grade 10, you would have been working with f at x equals -2 times x minus 5 squared plus 32. The only difference is how the problem is displayed, right? Because Quartic functions are a grade 12 problem. Don't need that $sign in here. Now example 3. So here again we're going to use our analysis skills. Now here we want to try and find the equation of the function from the graph. Okay, so we're going in the opposite direction here. Now again, just like in grade 10 when you were working with quadratics, when you were working in vertex form, we're working with an a value, a p value, and a q value. If you're not sure why it is we're always allowed to work without a k value, maybe just try and think about that a little bit, and if you get stumped, ask away in class next. You won't necessarily need to know that, but it's certainly something good to think about. Now, either way here, we're working, and we need to try and find an equation like that. Well, we're working with f at x equals, and we need to say, okay, the nice and easy ones to find here are p and q, because those are our translations. And we can easily find some identifiable points, not for every single cubic function, but for many cubic functions that are of this shape, the same shape as our base cubic function, in which case we may identify them by having a point of inflection in here where the slope is approaching 0 from the left and from the right. So here I have a point of inflection. This point of inflection is at the point 1, 2. We notice that this point of inflection has been translated from 0, 0. Because this point is not affected by the a value, this point has been translated 1 unit to the right, 2 units up. Nice and easy then. I'm working with a times x minus 1 cubed plus 2. Right, where I'm taking my 1 and 2 from this point of inflection. Now, just like you would have in grade 10, we need to find our a value. If we're going to find the equation of this function, we can find our a value by working with a point that we already know. Lucky for us, they've given us the point 0 and 5.5, so we can substitute in the point 0, 5.5. And folks, I encourage you to try this out, isolate for a on your own. I'm not going to do that because this is no longer a grade 12 question at this point. When you get there, though, I'll give you your final answer. So I'll say maybe pause if you don't want it spoiled for you here. Negative 3.5 is our value for a, x minus 1 cubed plus 2. That is our final answer here. Now, I did promise the video would be nice and short. These questions here I want you to think about as you prepare for class. We can talk about them in class, and in fact, we probably will talk about them by the time you watch this video, because this video is going up so late because the first iteration of this video had no sound. But I'm hoping at this point you're feeling a little bit more comfortable with some transformations of cubic and quartic functions.